Just a second, it's still setting up.
Sure.
And I think we should be good to go now. Thanks.
Okay. Okay, well, good morning, good afternoon, good evening, everybody. My name is Guido Roberts-Borsani. I'm a postdoc at UCLA working with Tommaso Treu. And today I'm going to talk about some of the work that myself and my collaborators, Richard Ellis, Nicolas Laporte, and now Tommaso, have been doing in trying to determine the stellar ages of the very first galaxies that appeared in the universe and try and pinpoint the timing of cosmic dawn. Now, this is a reionization conference, so I don't need to detail the history of the universe too much, but we know that over the first billion years or so of the universe, the very first galaxies and very first stars appeared, not in that order, and reionized the universe into what we see today. And so constraining the timing of this so-called cosmic dawn is especially important as this tells us something about the duration of the reionization process and ultimately the properties then of the galaxies that drove that reionization. We know that reionization ended roughly at a redshift of 5.8 or so, but we don't really know when it started. So can we probe this directly with the very first galaxies? Well, the answer is it's very challenging. The deep fields and cluster lenses have provided us with thousands of high redshift candidates, but only a handful or so have been spectroscopically confirmed. And unfortunately, we've reached the limit of what Hubble can probe with the dropout technique, since it probes only out to 1.6 microns or so. We can only look up to a redshift of 11, roughly. And Pascal Oche's object here at 11.1 is still the most distant galaxy we know of and is likely to be until the arrival of JWST. But is there something that we can do beforehand? Can we probe this indirectly? So, you know, can the ages and the star formation histories of redshift greater than 7 galaxies be measured? So at these redshifts, the rest frame optical is probed by the Spitzer IRAC channels, in particular 3.6 and 4.5. And at those redshifts, very strong nebular emission lines, in particular O3 and H beta, contaminate those filters, resulting in a very clearly defined trend as a function of redshift. So on the y-axis here, you're seeing the Spitzer IRAC color. On the x-axis, you're seeing the photometric redshift. And you can see at a redshift of 6.8, the O3 and H beta lines contaminate the 3.6 filter, making a particularly blue color. At a redshift of 7, those two lines transit over into the 4.5 micron filter, and H alpha leaves the picture. So you get this particularly red color over a redshift of 7 to 9. And then at redshifts greater than 9, those two lines exit the filter, so you get a relatively neutral color again. So crucially, at a redshift above 9, any IRAC excess, we call it, cannot be due to these nebular emission lines. So we went and we targeted one of these galaxies with the VLT, Next Shooter, and ALMA as well, found Lyman alpha and O3 88 micron detections, and crucially modeling of the HST and Spitzer photometry over here revealed that this IRAC excess could only be explained by a so-called Balmer break, resulting in stellar ages nearly about 300 million years or so. So we've continued those efforts with observations of other galaxies, but crucially now within this plot, we have two explanations for the color trends we see, either very strong nebular emission, as you can see in the top plot, from very young galaxies, or a so-called Balmer break at redshifts greater than 9, where you can see as you increase the age of the galaxy, the Balmer break becomes more pronounced and the IRAC color becomes more red. But what about at redshifts greater than 9, where those emission lines are still there? Are emission lines the sole reason for that IRAC excess? Well, we can now test this picture. We have over here the SED of a spectroscopically confirmed galaxy, which has been modeled as a nebular emitter. And you can see the IRAC fluxes over here boosted by the nebular emission lines. And we have our JD1 galaxy, the Balmer break one, where you can see the Spitzer excess is due to the Balmer break. We can mask those lines just to see the effect of the Balmer break on its own, and we can convolve those SEDs to the Spitzer bands over here and see what color trend results as a function of that. So you can see in red is JD1 and in blue is the nebular emitter. And you can see the nebular emitter follows exactly the trend that we'd expect, whilst the JD1 galaxy remains relatively flat until a redshift of 7.5 or so. And then you start seeing the effects of the Balmer break. And you start seeing this degeneracy, really. Remember that the emission lines here are masked. You see this degeneracy between the Balmer break and the emission lines, particularly at a redshift greater than 8 or so. And all these points are spectroscopically confirmed galaxies with this sort of IRAC excess. Now, to make sure that this is not primarily due to these two models, we can take simple stellar population models from Pegas 3 and plot as a function of stellar age what these might look like. And that's what you get over here. The very light blue curves are your very young stellar populations, whilst the dark curves are ones with more evolved stellar populations. And you can really see that it's not just this JD1 template that reproduces this. Crucially, just to show we can match all the IRAC excess galaxies, the dotted or the dashed line is our youngest model with extreme nebular emission. So is it possible to break this degeneracy prior to the arrival of JWST? The answer is yes, we can. ALMA can do this with observations of the 88 micron O3 line, which is tied to the O3 line at 5,007 angstroms. They are the same species, arrive from the same star-forming regions, as well as observations of the dust continuum can place constraints on what we would observe in the rest frame optical. So this is one spectroscopically confirmed galaxy, and the red is the measured photometry. And you can see the blue points are the fits with a young stellar population without including the ALMA data. You can see the Spitzer excess is well reproduced with intense nebular emission. But if we use the ALMA data, you can see through the orange points that actually we can't reproduce that Spitzer excess with extreme nebular emission. Essentially, we need an additional component, which would be that Balmer break. So we move forward then with our Pegas modeling, and we apply 1 and 2 component fitting, so a young starburst or a young starburst and a Balmer break, to the data of all redshift greater than 7 galaxies with an IRAC excess and that have ALMA 88 micron detections. Those are these 4 galaxies here, JD1, YD4, Y1, and B14. We include dust if there is a detection in band 7. And these are the results that we find. I'm only plotting 3 out of the 4 results over here. These are the 2 component fits. So the overall fit is in blue to the data, which is red. And then the 2 gray curves are your young stellar population and your older stellar population. The older one does not include nebular emission, but does include the dust if it's detected. And over here, you see the ALMA band 7 detections. And so crucially, you can see that the Balmer break is definitely required to explain the IRAC excess of these 3 galaxies. And you can see how the parameters of those galaxies change with the 2 component fits. The ages increase roughly by a factor of 10 to, increase from about 1 to 2 to maybe a couple of hundred mega years. The Balmer break is required for at least 3 of these objects, but when we account for the extra free parameters and the log likelihood, this reduces down to 2. We find that the stellar masses of these objects increases by a factor of 30 or so, and that for these 2 component fits, the nebular contribution to the IRAC fluxes is only roughly 10 to 30% or so. So what implications does this have for cosmic dawn? Well, there has been some tension in the past with data from deep fields and lensing clusters where we find they're in good agreement below a redshift of 8 or so. But above a redshift of 8, you start seeing perhaps some discrepancy between the 2 where it's not clear whether galaxies tend to form their stars more rapidly or at a more passive rate. And this would have implications for cosmic dawn, whether that occurred at a redshift 12 to 15 or so, or at above a redshift of 15. So if we assume the 2 component fits of all of our galaxies and take the mean, that's what you can see over here. These 2 curves that I show in the top panel overplotted, or similar ones are overplotted in blue over here. And our mean star formation history is here in red. It is only 4 objects, and there are questions about how representative these galaxies are. but you can see that they form roughly 44% of their stellar mass up to about redshift of 10, or prior to a redshift of 10, sorry. So are older stellar populations unexpected? I would argue not. We see from selection of Spitzer-Irac galaxies that there's an extremely high Lyman alpha detection rate. We also see that a lot of them have extreme radiation fields. We also find the presence of dust at very high redshift in these objects. Some AGN activity as well from detections of rest frame UV lines. We recently released a paper on the mass metallicity relation at redshift 8 and find that these more mass-heavy galaxies are in better agreement. And they're not uncommon in simulations either. So I'm running out of time, but future prospects, JWST will be able to solve or break this degeneracy, both with NIRSpec and NIRCam. This is the luminosity history of the JD1 galaxy, and you can see that it was actually brighter at redshift of 12 or so. So we'll be able to detect those progenitors. And this is a nice plot by Hutchison et al., who show what we can see with 2 hours of PRISM data. And here you see the O3 line, which contaminates the Spitzer-Irac filters. So JWST will be able to solve this. So I'll leave it here with my conclusions, and I'm happy to take any questions. Thank you very much.
Thank you for that, Guido. We have a couple of questions so far. The first one is from Steve, and he's asking, is there a simple scaling relationship between the O3 lines, or does it require more complicated modeling?
There is a simple scaling relationship with metallicity if you're talking about the ratio. So this is a plot I haven't showed yet, but what I'd like to draw your attention to, this is our young stellar population models as a function of time. The green line is the metallicity, and the O3 line ratio, 88 to 5007 angstroms, is this orange one here. And you see that it follows perfectly the gas phase metallicity in low electron densities and low electron temperature regions, purely because the 88 micron line is, does not change that much, but the 5007 angstrom line, once you start increasing the temperature, the levels required start getting populated a lot more, so you have a lot more 5007 angstrom flux. So it does correlate with metallicity, and I don't think you need more complex models than that. I hope that answers the question.
Very comprehensive. So another question from Dan Coe. What star formation histories do you consider?
Yeah, so that's a great question. Very simple one. So this is, let me just find. Right, so very simple ones. We can't model, of course, there are questions about when exactly, a galaxy forms. How do you define that? Here we're considering just the stellar histories. So for our two component models, we assume that this starburst ended at the redshift, of the galaxy, and that an older stellar population with a constant star formation rate of 10, 50, 100, up to 500 mega years occurred at some point before that, and that's left as a free parameter. Nebular emission is only included in the young component, whilst dust is included in the old component if there's that band 7 detection that you can see here. So the free parameters are the stellar mass then of the galaxy with those models. And we also include a free parameter to regulate the nebular emission so that we can get extreme nebular emission and at redshift greater than 7 probe IRAC colors up to about 1.4 magnitude or so.
Okay, I think we have time for just one more question. From Elizabeth Stanway, how well do we really know the metallicity of any galaxy at these redshifts?
I mean, I don't think I'm the best person to answer that. This paper doesn't focus necessarily on the metallicity, but what we do check to ensure that, for instance, our O3 ratios, which I just showed here, to ensure that our O3 ratios probe, a suitable range, is check that our metallicities of our models of our young models are consistent with what we see in the local universe. So we compare them with the results from the dwarf galaxy surveys and find that we probe, gas phase metallicities of about sort of 0.4 to solar consistent with what we see in the local universe. So I can't answer, just how robust those are, but they are at least consistent from the modeling perspective with what we see in low redshift, similar galaxies.
Great, thanks for that. There are a few more questions on the Slack channel if you don't mind answering them at some point in the future.
Sure, I'll do that. Thanks very much.
Okay, so our next speaker today is Taylor Hutchison, who's going to talk about near-infrared spectroscopy of galaxies during reionization.
All right. Sorry if you hear a train in the background. There's one going by. All right, hi y'all. I am Taylor Hutchison, and like they said, I'm going to be talking about near-infrared spectroscopy of galaxies during reionization. So we've heard a lot of really good talks already, kind of motivating why we all care about this particular subfield of extragalactic astronomy, and in particular highlighting the usefulness of the Lyman alpha mission line for probing the Epoch of Reionization. So to just kind of springboard from that and jump right in, Lyman alpha is a really useful tool for looking at these galaxies in this epoch. However, there are some complications with it. It's a resonant line, it's subject to scattering, can be heavily attenuated by neutral hydrogen, and often the redshift you derive from the Lyman alpha emission line can be hundreds of kilometers per second redward from where the true redshift actually is. So here's a beautiful example of this. This is a Lyman alpha spectrum from Dan Stark's work in 2015. And you can see this asymmetric shape, and the blue dashed line is the redshift you derive for Lyman alpha. Notice that it is offset from where the systemic redshift for the source would be, which is the red dashed line. And so obviously this kind of pushes that there's a need for a systemic tracer. And ideally, the criteria you'd want to meet is your systemic tracer should not be attenuated by neutral hydrogen or outflows, should represent the true redshift of the source, and ideally, be in the ultraviolet because we're working with galaxies in the Epoch of Reionization. So some of your best bets are going to be some of these red lines I'm pointing out. So carbon-4, PM2, O3, and carbon-3. However, your true best bet for the Epoch of Reionization is most likely carbon-3, as it's often the second brightest line in the UV after Lyman alpha, and also is really ubiquitous in these high redshift galaxies. And so once you have a systemic redshift and a Lyman alpha redshift, you can compare the two and come up with this measurement for the Lyman alpha velocity offset, which is the equation on the bottom, which can give you insights into the kinematics of the galaxy and possibly whether or not there's neutral gas as systemic. All right, and additionally, with these UV metal lines, there are also powerful probes for stellar populations, the type of ionization and the strength of it that's in these galaxies, and then also the chemical enrichment that's happening in these galaxies. So to start off, there's a quote unquote pilot study that we did. So essentially the way the process worked is we took a galaxy at redshift greater than 7 with Lyman alpha that was spectroscopically confirmed. From there, we do follow-up spectroscopy targeting the carbon-3 doublet, which is a 1907, 1909 angstroms, to try and find systemic redshift. If possible, if it's in the same wavelength region, we also would try and target the silicon-3 doublet. From there, we measure the systemic redshift compared to the Lyman alpha redshift, and then adding in available photometry and any other ancillary data compared to photoionization modeling to walk back for low metallicity, high ionization models, what kind of galaxy properties might best match our observed properties. So the galaxy we chose in particular is this one originally detected by Steve Finkelstein in 2013, Lyman alpha redshift of 7.51. You can see a poster stamp of it on the bottom left. This galaxy has an IRAC color of 0.8 magnitudes, fairly red, but as you just saw in Guido's talk, this might not be unexpected. And so we did some follow-up spectroscopy in H-band with the Keck Mossfire spectrograph, and you can see the spectrum on the right-hand side. We definitely detected carbon-3, but as you might notice, it's a doublet, and we're actually only seeing one part of this doublet. Unfortunately, it's so perfectly placed between these two skylines that whichever part of the doublet it is, the other line falls behind one of these two skylines. So by eye, it makes it challenging to determine which part of the doublet we've actually seen, but through comparison of other measurements that we have and also work from the literature, we've determined that the line we most likely have is the 1907 part of the doublet. However, I'll also show you solutions for if it's the 1909 line. So from this detection, we can get a systemic redshift for the source of 7.5032, which yields a Lyman alpha velocity offset of 88 kilometers per second, which is very small. This likely implies that there's hard ionizing radiation, it's systemic, that's likely clearing out some neutral hydrogen, allowing Lyman alpha to escape closer to the systemic redshift. From assuming a line ratio of the two parts of the carbon-3 doublet, we can get a combined line flux, which then can provide us a rest frame carbon-3 equivalent width for the line. And this gives us, it's 16 angstroms, which is strong, but again, not really unexpected for these young, highly star-forming galaxies in this epoch. So from there, we compare with our photoionization modeling and any available photometry. So as we saw in Guido's talk, a really good tool you can leverage at redshift 7.5 is the fact that you have O3 and H beta popping up in the 4.5 band. In this case, we actually enjoy this possibility. And so for the 3.6 minus 4.5 IRAC color, what this means is there's nothing in the 3.6 band. So you can essentially see this color kind of as a proxy for the O3 and H beta equivalent width. This is what we're showing you on the x-axis. On the y-axis, we have the rest frame carbon-3 equivalent width. And so for each of these subpanels, you're seeing a range of different models where we're varying on the left-hand side, for instance, we're varying the color, which shows this change in stellar metallicity. The line type is this change in nebula metallicity. And then starting at the bottom left and going up to the top right, we have an increasing ionization parameter. And so what you're seeing on the left-hand side are the B-pass stellar population models with binary stars involved and an upper mass limit that extends to 300 solar masses. And you can see that there's pretty good agreement. It covers a lot of these different types of models seem to cover the space occupied by the dark red star, which is the preferred solution that the line is in 1907. The light star is if the line is 1909. On the right-hand side, you see stellar population models using starburst 99, where the IMF only extends up to 100 solar masses. And you can see that very few of the models seem to reach into the space occupied by our galaxy, at least within 1 sigma, so you're kind of seeing these two different extremes with these two different stellar population models, and kind of highlighting that the most likely matches for this galaxy are these low metallicity, high ionization galaxies that have really strong, that have possibly disconnected stellar metallicity and nebula metallicity. So additionally, I mentioned that we were looking at the silicon-3 doublet. It was actually not detected in our H-band spectrum, but that's actually fine because you can actually still get some really interesting information from non-detections. So we placed an upper limit on silicon-3, and then by taking a ratio of silicon-3 to carbon-3 and comparing it with our modeling by varying the ionization parameter, which is the x-axis on this plot, you can see that as the ionization parameter increases to the right, this ratio drops. And it also seems to be more heavily affected by metallicity towards the higher ionization. So what you can see here is even with the upper limit, where we don't actually have a detection of silicon-3, we still seem to find agreement that this modeling suggests that the galaxy most likely has this high ionization and low metallicity, which is in really good agreement with the separate measurement of the carbon-3 equivalent with IRAC color, which is really exciting. So there's some really useful information you can get from literally 1 detection and some upper limits. So the current work is kind of building off of this. So taking all of that information and the techniques that we use, but now extending it to do a broad sample of galaxies from the literature, from redshifts 5 to 8 that have Lyman alpha measurements, spectroscopically confirmed. And of course, we'll also have a photometric sample as well. So there's also a priority sample from redshift 6.8 to 8, which I'll explain why it's priority in a second. But yeah, so it's work as usual. We're going to target these rest UV emission lines. Now we're extending to all of them, and then kind of follow the same procedure and try and pull out information, any information we can for these galaxies. Just as a note, a detection of more than one of these lines for a particular galaxy can provide significantly increased constraints on the possible stellar population properties for these galaxies. And like I showed you before, even non-detections can provide some really valuable information. So the current program, we are using Keck MOSFIRE to target these rest UV and nebula emission lines in galaxies from 5 to 8. The priority sample is actually really exciting. So I realized that with MOSFIRE, there's this sweet spot in redshift where you can get from 6.8 to about 8, you can get some number of lines in the MOSFIRE J band, and then some number of lines simultaneously in the MOSFIRE H band. So for instance, what you're seeing in this plot here is a simulated stack of MOSFIRE data showing just some of the UV lines that we care about, and then overimposed are the MOSFIRE J and H bands that are de-redshifted, but showing what you see for redshift to 7. And so for redshift to 7, you could potentially get carbon-4, helium-2, and O3 in the J band, and then simultaneously get silicon-3 and carbon-3 in the H band. Now, it's important to note that a lot of these lines might be really faint, but still, even non-detections, like I pointed out before, can provide really interesting constraints. So for this program, we have been awarded 8 J-band nights in 2018 and 2019 for Rebecca Larson's work, PIing, targeting these Lyman alpha emitters at redshift 9 and greater. This work was done as a secondary science case for that program, and so we were able to look at redshift 5 to 6 targets, targeting the carbon-3 and silicon-3 emission. And then we now have an additional 4 nights awarded in 2020 for this full J and H band program, which is really exciting. And so we have some exciting preliminary results, but also just as a shout out, Rebecca Larson's done an amazing job with the data reduction process and analysis. And so you should definitely keep an eye out for her upcoming work on that. So to kind of show you a few preliminary results, on the left-hand side, I'm showing you just a cute serendipitous O2 detection in one of our spectra. This is this is what we wish we could see at this redshift. But this is showing you, very beautiful doublet detection and also the unique signature of the Mossbauer data because of the dithering technique we use. And so you'll have a positive trace in the middle and then a negative trace above and below. This is real things will have this trace. So just to show you a handful of some of the tentative detections of UV lines at redshift greater than 5 that we have, here's just showing you a handful of them. I'm being coy and not telling you what they are or the redshifts that they have because I want you to stay tuned. We'll be showing you them in the future. So this is all preliminary work as a note, but it's really exciting. We're already getting some results and hopefully we'll be able to get these analyses done and these answers to you as quickly as we can. But just kind of as a plug, Guido already showed it, which is wonderful. But James Webb, we kind of have to talk about how amazing it is. Or at least I feel like I need to. It's going to revolutionize what we do, as we know. But I'm just particularly excited about the implications for the nebulae physics you can do with it. And so, for instance, as he showed, this is a thing I ran through the ETC. This is just showing some of the models that best matched the galaxy from 2019. And you can see that with 2 hours on the prism, with a resolution of about 100, you can get from Lyman alpha all the way out to optical O3. And now, of course, some of the lines are blended, but even some of these detections can just open the door for this playground of nebulae physics. And it's just really exciting. So I hope, knock on wood, that goes up soon. And so, yeah, so I'll leave up my summary slide and I'll take questions. Thank you.
Thank you for that, Taylor. So just waiting. Doesn't appear to be any questions at the moment, which is a new one. Oh, sorry, my computer was just taking a while to update. So we have a question here from Rebecca Bowler. Could you explain more about how the sample was selected? Could it be that very strong line emitters be excluded by these criterion?
That's a good question. So for now, the sample is just chosen from photometric sources that from photometry and with SCD fitting that seem to match the redshift range we care about. We're not getting specific on trying to do selections by estimated stellar mass or anything. And then the main sample are from sources that have been spectroscopically confirmed for Lyman alpha. So there obviously is a bias here. They have to be spectroscopically confirmed via Lyman alpha. So this tells you a lot about what the galaxy might be like. So we're definitely not going to be using this as a indication for galaxies as a whole, these redshifts. But yeah, that's mostly where the samples are coming from.
Okay, great. Another question here from Michaela Bagley. This is quite a long question, so hopefully I'm going to read it out properly. If you allow the stellar IMF to go up to 300 solar masses, then the metal yield ratio of silicon to carbon is supersolar, which is already expected at high redshift anyway because of the weak contribution from AGB stars at early times. Does the analysis of the silicon non-detection allow for non-solar abundance ratios?
That's a fantastic question. So for that particular work from 2019, we didn't actually explore anything past assuming solar ratios, but that is definitely work in the future with more lines. Ideally, I would like a detection of silicon-3 to really do that analysis. But yes, that's definitely the next step, is looking into the variations of abundances, including those kinds of relationships, yes.
Okay, great. Thanks again, Taylor. I think we'll leave it there. We're just about running out of time. So our next speaker is Jorge Zavala, who's going to tell us about constraints on the dust-obscured star formation up to the Epoch of Reionization.
Okay, can you see my presentation?
We can, and we can hear you.
Cool. Okay, well, first of all, I'd like to thank the organizer for doing this meeting and also for giving me the opportunity to talk about this result. This is a work that we have done as part of the Cosmos collaboration, and we are going to present basically some constraint or estimation of the dust-obscure star formation rate density up to redshift 6.5, which is close to the epoch of reionization. So yeah, let's start with the cosmic history of star formation. So in this plot, we have two different kind of measurements of this quantity. One illustrated here in blue comes from UV, an optical observation, which traces the unobscured component of the star formation. So these measurements are actually, we have good constraint up to redshift of 8, and we have some measurements up to redshift of around 10. On the other hand, we have the constraint that comes from far infrared and submillimeter and millimeter observation, which traces the dust obscure component of the star formation. In this case, we have good measurements of this quantity up to a redshift of around 2, which is close to the peak of the cosmic star formation rate density. And beyond redshift 2 or maybe redshift 3, we have like just incomplete measurements of this quantity or very highly uncertain estimation. And beyond redshift 5, we have basically no constraints on the dust obscure star formation rate density. So the main goal of this work is to constrain the dust obscure component of the star formation rate density at least up to at redshift of 6. One thing that we need to highlight is that the current data or the current constraint cannot distinguish between these two different extreme scenarios. So in one scenario, we have this line here, which illustrates a universe in which dusty galaxies basically do not contribute significantly above redshift of 4. So basically, the star formation rate density is dominated by the unobscured component. But on the other hand, we have this other scenario in which dusty galaxies dominate the star formation rate density even up to a redshift of 6. And there have been some works in the literature that suggest that the universe could be either of these two different scenarios. So the current data cannot distinguish between these two very extreme scenarios. So this is the goal of this work, is basically using all the observation at far infrared and submillimeter and millimeter wavelengths, and particularly in this case, the number counts, to constrain the infrared luminosity function, and with this, constrain the dust obscure star formation rate density. So we are going to use the number counts as a constraint, and we are going to use a backward evolution model to do this constraint. So I'm going to describe just briefly how the model works and how we infer these constraints on the dust obscure star formation rate density. So basically, we start with an infrared galaxy luminosity function, which looks like this sketch. The infrared galaxy luminosity function is actually well constrained up to redshift 2 or 3, but beyond redshift of 3, we have like no good measurements of this quantity. So we use the infrared luminosity function that are well constrained below redshift 3, and then beyond redshift of 3, we just explore different evolutionary model for the infrared luminosity function. So once we have a model for the infrared luminosity function and its evolution, we combine this with a library of spectral energy distribution. This is just basically for the dust emission of the galaxies, and our SEDs follow this relation, which is the dust temperature relates with the luminosity of galaxies. So with these two components, we can explore how many galaxies we have as a function of luminosity, as a function of redshift, and we can estimate the flux densities at different wavelengths using the SEDs. So with combining these two quantities, we can create fake observation or fake maps at different wavelengths. This is just an illustration of 3 different wavelengths at three different maps at 3 different observations. And then we can combine these fake maps with a beam size, so we can try to mimic the real observation, and we can add noise to our fake maps just to reproduce real observation. So these are just some example of the result of this model, which these are fake observations that resemble the real observation, real telescope surveys. So once we have this fake observation or simulated observation, we can extract the sources from these maps and then measure, for example, the number counts in these maps and compare the number counts to the real number counts in the observation. So this is an example in which in orange, we have the number counts from the model, and in gray, we have the real number counts from a real observation. And we can see that the model do not reproduce well there is a discrepancy between the model and the observation particularly in this regime. So we can go back to our model and now change the evolution of the infrared luminosity function at high redshift and repeat again all the process. And then we can get a different number counts. And in this case, the number counts fit the data. So in this way, we can use these statistical measurements, the number counts, to constrain the infrared galaxy luminosity function. So we have done this, and these are just prediction from the model for the number counts at different wavelengths. These are two extreme scenarios. In one case, in blue, we have prediction for the dust-poor universe, in which basically dusty star-forming galaxies do not contribute significantly above at redshift of 4. And in orange, we have prediction for a model in which dusty galaxies dominate the total star formation rate density, even up to a redshift of 6 or 7. So as we can see in the first two rows, the prediction from the two different scenarios are basically the same at short wavelength. And this is because the infrared luminosity function at low redshift for the two models is the same. Just the infrared luminosity function is different just at high redshift. And since at short wavelength, most of the galaxies are low redshift galaxies, the prediction are basically the same. And we can see that the model prediction are different for long wavelength observation, particularly 1 millimeter and 2 millimeter. So basically the conclusion for this test is that long wavelength observation, particularly longer than 1 millimeter, are ideal to constrain the infrared luminosity function at high redshift. So this is one of the reasons of why we propose to do this ALMA blind survey. This is the MORA survey, which is the first ALMA blind map at a wavelength of 2 millimeter. And as we can see, it's a relatively large map compared to other ALMA surveys. This is 185 square arc mean of observation at 2 millimeter. And here as a comparison, I'm showing just other ALMA maps. So we did this in ALMA cycle 6, and these are just some examples of the sources that we have detected. We have a sample of 13 sources above 5 sigma. We have some spectroscopy redshift for some of them. For example, we have this galaxy at redshift 5.8. And basically all the galaxies that we have detected are above a redshift of 2. So we have used this sample of galaxies and we have built the number counts at 2 millimeter. And then we have used these 2 millimeter number counts to constrain our model and the infrared luminosity function in our model. So the 2 millimeter number counts are here in the middle, but we have also used the 1.2 millimeter number count from the ASPEC survey, which is also a very deep ALMA survey. And also we have used the 3 millimeter number count from this paper that I published like 2 years ago in combination with the ASPEC results at 3 millimeter. So we have 3 different number counts at long wavelengths, and we have used this number count as a constraint for our model, which I described before. And basically the prediction or the best fit model that better reproduce the number count simultaneously are these gray lines. So we can see that the model does a very good job at reproducing these 3 number counts simultaneously. And the model also reproduces the number counts at shorter wavelength. These are just some examples of 250 micron, 500 micron, and 850 micron. So now with these number counts, we have a well-constrained model. So we have a relatively well-constrained infrared luminosity function. And now we can just integrate the infrared luminosity function across redshift and derive the star formation rate density, or at least the dust obscure component of the star formation rate density. So the prediction of our model or the constraints from this model are illustrated in this orange region. There is, of course, like the peak is at redshift 2, which is between 2 and 2.5. And then the dust obscure star formation rate density declines at high redshift quite significantly. And here, just as a comparison, these are just results from the literature. So we can also break down this star formation rate density in luminosities. And we can see that most of the star formation rate density of this dust obscure star formation rate density comes from LERC and EoR galaxies, which are relatively massive and bright galaxies, which is in contrast to the UV optical unobscured star formation rate density, in which a large fraction of these come from faint galaxies. So here we have relatively massive and bright galaxies dominating the star formation rate density. So we can also plot on top the constraint from the UV optical surveys, and we can see that the dust obscure and the unobscured component basically have a comparable contribution between redshift 4 and 5. So we can divide this or just make the ratio between these two quantities and estimate the fraction of obscuration in the star formation rate density. And we can see that the dust obscure star formation rate density basically has dominated the star formation, the cosmic history of a star formation up to redshift 4. I mean, there are some uncertainties in this measurement, but beyond redshift 4, or well, let's say beyond redshift 5, the dust obscure star formation rate density is most likely not the most dominant component here. And beyond redshift 6, basically the dust obscure star formation only contributes around 20% of the total cosmic star formation rate density. So with this, we have kind of a complete picture of the cosmic history of star formation from redshift 0 to redshift 6.5, which is quite a high redshift for this measurement, particularly for the dust obscure component of the star formation rate density. And I think my time is up, so I just finished here. Thank you.
Thank you for that, Jorge. So there's a few questions just coming in here. So Tom Toons asks, could you include AGN in the modeling? Would that make a difference to your conclusion?
Yeah, basically in the model, we have no AGN here, basically because we are just trying to reproduce the star formation, I mean, just the emission of the galaxy that comes from the star forming region. And we know that for the number counts at 850 microns and longer wavelengths, most of the galaxies are dominated by star forming galaxies. And the AGN contribution is like a minor fraction. We could probably introduce AGN, but this will probably change the number counts and prediction from our model. And now then the number counts agree with the data basically for all the wavelengths. So if we introduce AGN, we probably will have some disagreement with our model and the data.
Thanks, that's great. Mark Dickinson asks, on your slide from the infrared luminosity function to the cosmic star formation density, at redshift 4 to 6, what are those measurements?
Okay, yeah, I mean for the infrared data points, I don't have all the reference here, but basically come from the Madao compilation plus new measurement from McNally et al., Kaprowski, and Williams. I mean, I don't remember all the reference. And the blue region comes from Finkelstein 2015 paper, which is also the UV measurement that we adopt. But basically, it's the Madao compilation for both the IR and the UV plus new measurement from the literature. I can give you the full reference offline.
Great, and I think just time for one more question from Roderick Overzire. What fraction of the infrared obscured star formation is accounted for by correcting the reading and correcting the UV measurements? So I guess if you applied the kind of beta IRX calibration, what fraction of that star formation do you recover?
Yeah, I mean, I haven't done particularly that specific calculation, but here the UV measurement that I'm plotting here, these are not correcting for dust. And we can have just like an idea of the fraction of obscuration, but for the total star formation based on this top panel. But I have not done the calculation specifically for what would be the correction that we will need to do for the UV in order to match the total star formation rate density. But I can also chat offline about that.
Yeah, there's a few more questions on the Slack channel, but I'll let you answer them in your own time.
Cool. Yeah.
Okay, so our next speaker is Sultan Hassan, who's going to tell us about whether can galaxy evolution mimic cosmic reionization.
Yes, hello. Can you see the slides?
Yes, we can see you and hear you.
Okay, sounds good. Okay, so my name is Sultan Hassan. I'm currently in New Mexico State. I will be joining the Flatiron in a few months, and this work is in collaboration with Max. He's currently now at Johns Hopkins. So this work is basically about our understanding about galaxy evolution and how that can impact our understanding also of Lyman alpha observation. So let me just start. Let me start by showing this plot. This is our most updated constraints about Lyman alpha fraction. What you see in the y-axis, basically, this is the abundance of Lyman alpha emitters, if you want to say, evolution as a function of redshift. And these all are the measurements. What you see here is that the abundance increases up to redshift of 6, and all of the sudden there is a drop here. And this drop is very interesting drop because it has been mainly used to constrain our understanding about the IgM and the neutral to estimate the neutral fraction of the IgM. And so the idea here is that whether we can, is it really due to the IgM or something else? So this can only be valid, this drop in the abundance, if galaxies themselves do not evolve. So if we don't have any evolution in the galactic properties, in their column densities, outflows, in their all the properties that they have, they stay fixed or they have a minimal evolution, then you can safely say, yes, this drop is really due to the IgM and reionization, right? So this is the main idea of the talk. We want to see the conditions by which galaxies, the evolution in galaxies themselves, can really reproduce this drop. So just to see like the basic arguments here. So this equation relates the observed Lyman alpha luminosity with the intrinsic luminosity, and this relation is set by the transmission in the IgM, and this is how basically the idea of getting like the observation of Lyman alpha, the drop in Lyman alpha abundance or fraction by using this transmission in the IgM to try to quantify the neutral fraction. However, there is this component is the F-escape, which is highly debatable in high redshift. It's least constrained at these high redshift epochs, and it mainly captures the physics of the ISM and also for the CDM. So this is here the goal of the talk and the work is to see, to fix the IgM. We don't really change anything about the IgM. We assume it's fixed, and we want to change how the galaxies behave, right? And their behavior is set by their galactic properties. So in order to do this accurately, you need to model the ISM. The ISM is very complex to model, and it's very expensive. And at the same time, you need some models that really explore broader parameter range very quickly. So we use this shell model. It's Monte Carlo radiative transfer. Run on a shell model, so you assume all galaxies are shell, and in that shell you have an expanding velocity. This is the outflow velocity that we expand, and you have also the amount of neutral hydrogen. So we want to change this, and we want to see how the F-escape would really mimic the behavior of reionization here. So then if you do the calculation of the Lyman alpha fraction and you go through the equation, you would realize this drop, if you want to reproduce the drop from redshift of 6 to 7, it's really equivalent to the drop if the F-escape goes to its half value. So if you have a reduction in the F-escape by half, so you would assume that all galaxy population, all of the sudden just they reduce their F-escape by half. And this is reasonable also assumption, because we see that from previous talks now, people do require an evolving F-escape to match the constraint. So it's really, nobody really knows whether it's evolving or whether it's really constant. And so if you want to match the redshift of 7, you can say it's dropping by half. Probably if you want to match, if you want to start from redshift to 6 to 8, maybe that might be a drop by a third. But at the end of the day, let's say it's half to redshift of 7, and we want to see these conditions. So if you, this plot now, when you run the shell model and you change your parameters for different amount of dust and for different outflow velocities, you would see that the general behavior is that the F-escape goes down as you increase your column density, of course, because you are going to denser regions. Different column, different dust, of course, dust, as you increase the dust amount, because the dust destroys the photons, right? So then you have reduction in the F-escape as you go down. The outflow velocity would increase your F-escape, so there is a degeneracy between these two effects here. But the main idea is that the factor of 2 is really possible. It's not really possible if you look at the very little amount of dust. It's very hard to reproduce this factor of 2, but any amount of dust that is higher probably than 0.2 in optical depth, you might be able to get the factor of 2. For example, if you look at column density at 10 to the 17, you get by 0.04 if you're following this line, red line. Then if you increase the column density up to close to 10 to the 19, you get the factor of 2. So it's possible to change that. However, the change here is huge if you start from a low column density, but if you go to a very high column density, the change is very small and you should be able to reproduce the observation. So the idea here is that the factor of 2 by changing the column density is entirely possible. However, you can do the same experiment by looking at how the outflow velocity changes, different colors, different dust amount. Of course, the dust reduces your F-escape. And the photon escape fraction here, you see that it increases as the outflows. If you have a more expanding shell or have the galaxies, the outflows is higher, then your F-escape goes higher. So then it's also with a little dust, it's very hard to reproduce the amount of a factor of 2 in F-escape or factor of 3 if you want to go to redshift of 8. But then if you follow this dashed blue line, let's say for different column densities, like this is a column density of 10 to the 20, you realize that you need outflow velocity probably close to 300, but then if you reduce that to less than 100 or close to 100, then you might be able to reproduce that drop. So it's again, but here you have to go the opposite way. So you need to start at redshift of 6 in a very high velocity, and then the velocity drops, and therefore you get a very drop in the F-escape that mimics reionization, basically. So also changing these galactic properties does not only change your F-escape, but also it changes the spectral shape line. And this is something also, it can be tested with the observation, right? So what we see here in this plot, this is the Lyman alpha line for different models at 6 and 7. And for different column densities that they for a fixed amount of dust and velocity. And you see this model, they do have a difference of half escape fraction, so they do mimic the behavior of the Lyman alpha drop, the observed drop. And therefore, what you see when you increase your column density, you are increasing the width of the line, right? So it's something that can be tested. You can see this behavior. If you see that behavior in the observation, you know that now when you increase your column density, all of a sudden your line increases, the width increases, right? However, from the observation, what we know is that it's the opposite scenario to changing the column density. This is the candle survey. And for this spectrum, what you see here, this is the stacks at redshift of 6 and 7. And what they show here, the lines are highly asymmetric. And if you look at their equivalent width, you realize broader lines. You have like at redshift of 6 about 300 kilometer per second, and at redshift of 7 about 220. So it seems like the observation indicate that you have a broader line at lower redshift, right? And this is really in opposite way what we have seen with the column density. However, you can get it right if you change your outflow velocity. So the outflow velocity would reduce your width, and this is what you see here. You have two models of 6 and 7 for different outflow velocity, nearly 140 and 40 kilometer per second for a fixed amount of dust, of course, and a fixed column density. So what you see here is that when you, this is not also a consistent comparison with the previous plot, because that one was a stack stacks of spectra. This is only one run. But it gives an idea, and the example is that the changing galaxies can really do the same. So if you look at the spectral shape at redshift of 6, you realize your FSK is about 0.26, but then your width is about 300, which is the same thing that we have seen now from the observation at redshift of 6. When you change the outflow velocity by a factor of 100, you reduce that by a factor of 100, your FSK goes down by 0.12, so it's nearly half that reproduces the drop. And at the same time, you get the width of this red peak is really the 220 kilometer per second, which is consistent really with this. It's not really consistent because it's not one-to-one comparison. As I said, these were stacks, but it gives an idea that the outflows can really reproduce this drop. And I would like just to mention here, it's very interesting that this blue peak appears by redshift of 7 as soon as you reduce your velocity, outflow velocity. So just my takeaway here, because of the time, it's really possible to reproduce the observed drop just by galaxy evolution. The galaxy evolutions can also, changing these galactic properties, can really change the Lyman alpha spectra, which can be tested with the observations, right? And we would, and I guess to accurately estimate the neutral fraction and estimate cosmology from Lyman alpha observations, one need to take into account these potential changes, which with more data sets and more samples and more spectra in the future, we should be able to map this spectral line changes with the galactic, with the change in the galactic properties. And with that, I stop here. Thank you.
Thank you very much, Sultan. We've got a few questions already on Slack. So I'm going to start off with the highest ranked one, which is from Tontoons, who asks, why would the Lyman alpha fraction decrease again towards lower redshift? i.e., why is there a peak at redshift 6?
I guess that is also support the idea that the IgM because the universe is neutral, is more ionized, then you can see these Lyman alpha emitters, right? But at the same time, what we are saying here is that it can be also dual effect, right? So a change in the galactic properties with the change in the IgM together can explain these possibilities, right? So so I guess just my answer here is that it's possible that the IgM is doing the job. That's because it's ionized, you can see many of them, but at the same time, it might be also possible that we have contribution from a change in the galaxy evolution.
Thank you. And another question here, this time from Maxime. Do you have any sense for how your model will be affected by a more complex geometry than a homogeneous shell? For example, a shell with holes or with a velocity gradient?
Yeah, that of course will highly impact the F escape. But these models, yeah, so it will only affect, I guess it will affect our, like the estimation of the F escape fraction, and then it will be interesting to check that. However, it's very hard to model, like if you want to explore a large parameter space of these models, ideally, it's very hard to do that with an accurate ISM simulations. You wouldn't be able to explore that large parameter space very quickly. You need to run it for month and month, and it takes very long time. So this is here to give a quick idea about how it's done. But of course, it would be interesting to see that change when you have more idealistic environment, which of course it will change how the F escape behave, of course.
Okay, I think time for one more question, this time from Charlotte Mason, who agrees that it's really important to take into account the intrinsic evolution, but do you have a physical interpretation for why these properties would evolve so rapidly during this time period?
Well, again, I mean, there are so many uncertainties here, right? So we don't know, we don't know much about the F escape. We don't know about how the dust, how the metallicity changes. So all these things is it's very interesting to understand more with the future observations. But but it's really from the models of reionization that we have seen now, an evolving F-escape with redshift is entirely possible. One would imagine, no, why would photons really care about the time by which at which they emit it, right? It doesn't really make sense. But then the models, many models of reionization do really include an evolving F-escape to match the observation. So the idea that the photon escape fraction for galaxies populations should change with time, it's an idea important for many theoretical models. And because of the uncertainty in the F-escape, we don't know much about this. So it's possible that, and we have seen now changing only two parameters. One can change other parameters, possible other parameters, if you have more complicated models, and then you should be able to disentangle these effects and see which effect is leading more. But with this simplified model, it's very hard to explain the observations with only two parameters. You need probably more ideal simulation to do so. But this gives us like first order approximation of what could happen and what should change, right?
Thank you again, Sultan, and apologies to everybody who asked a question, but we didn't have time for. Hopefully Sultan will be able to answer them on Slack. Okay, so our next talk is from Javier Álvarez-Márquez, who's going to tell us about investigating the physical properties of galaxies in the Epoch of Reionization with JWST MIRI spectroscopy.
Hi, everyone. I am Javier Álvarez, and I am working in Centro de Astrobiología in Madrid, Spain. And I would like to talk about investigating the physical properties of galaxies in the Epoch of Reionization with MIRI and JWST spectroscopy. I am part of the MIRI European Consortium team. And here is the outline of my talk. And I would like to describe the MIRI instrument and focus on the medium resolution spectrograph that will be the mode that we will use to perform the high redshift spectroscopy GTO program. That is, I will summarize in the point 3, and then I will show some simulation of high redshift GTO sources that we will use MIRI Sim. That is the MIRI instrument simulator that has been created by the MIRI test team. And then I will show two examples of star-forming galaxies and quasars. And then I will summarize the talk. And the James Webb Space Telescope has 4 instruments, and in 2 different modes, that is spectroscopy and imaging. And there are 3 of them that cover the visible to the near infrared. And then we have MIRI that cover the mid-infrared part of the cover from 4.9 to 28.8 microns and have 4 different observing modes. One is the imaging. The second one is the integral field unit spectroscopy. That is the one that we will describe in the next slides, because the one that we will use for the high redshift GTO program. And then we have 2 more modes, that is the slitless spectroscopy and the coronography. The MRS, that is the only James Webb spectrograph that covers from 5 to 28 microns. And it is an integral field spectrograph that he has 4 channels. And each of the channels is split in 3 sub-channels, as you can see in the bottom panel here. The field of view are from 4x4 from channel 1 to 8x8 to channel 4. The slide is 0.2 to 0.6, depending on the wavelength, and his spectral resolution are from 3500 to 2500. And the spectral resolution, the spatial resolution is lower than the arc seconds. The MRS combine new and unique capabilities to study high redshift galaxies. And for example, his continuous coverage from 5 to 28 will allow to study the rest frame optical and near infrared range in high redshift galaxies. For example, the H alpha emission line will be observed for redshift higher than 6.7, and the 8 beta and oxygen 3 will be accessed to for galaxies at redshift higher than 9. His spatial resolution will allow to study physical scales of 1 to 2 kiloparsecs for redshift higher than 1, and his spectral resolution will allow to disentangle velocity structure close to 100 kilometers per second. And his sensitivity will allow to detect fainter and higher redshift galaxies. Here I present the high redshift spectroscopy program of MIRI. We have selected 9 galaxies. It is a sample of different type of spectroscopically confirmed galaxies within the first gigayear of the universe. We have 3 different blocks. The first one is the star-forming galaxies, that we have 4 galaxies between redshift 7 and redshift 9, and we will target H alpha. Then we have the quasar, that we have 2 quasars at redshift higher than 7, and we will cover the full spectral range of MIRI, and we'll be able to detect the continuum and optical and near-infrared emission line for these 2 quasars. Then we have the dust star-forming galaxies. We have 3 of them from redshift 4 to redshift 6.9, and depending on the redshift, we will target H alpha and or near-infrared emission lines. The total amount of time of this program is 65 hours, and all the sources will be also served by the NISPEC GTO program. This means that we will have access to other emission lines. Now I will take 2 of these blocks. I will take B14 and 1 quasar to perform some simulation and show to you how this will be seen by the MIRI. I use the MIRI instrument simulator that is called MIRI-SIM and has been made by the MIRI test team. This reproduces the on-orbit MIRI JWST observations and include all known detector characteristics. This is public and can be used by the community. Then the simulation from MIRI has to be calibrated using the official JWST calibration pipeline. The first example is B3 Dragon, B14. That is a UV bright system of 2 sources likely interacting or merging. These are a galaxy at redshift 7.15, have a star formation of close to 200 solar masses per year, and a stellar mass close to 7.7 to 8 to 10 to 8 solar masses. This has been detected in emission lines, far infrared emission lines, 3+ and oxygen 3, and also by dust. And here is the simulated H alpha map of this galaxy using MIRI-SIM and a 40 kilosecond observation. And this has been published in this paper at 2019, Álvarez-Márquez 2019. And if we extract the spectra of each of the clamps from channel 2 and channel 2 of the MRS, this is the result. And we have simulated each of the clamp with a different metallicity to see the difference in the spectral features. We will have access to nitrogen and sulfur emission lines, that these are sensitive to the metallicity. Then if we combine hydrogen emission lines, will be sensitive to the dust extinction. And also if we combine with helium and H alpha, we will be sensitive to the hardness of the ionized radiation source for these galaxies. And for them, I would like to show simulation for a quasar. This is a 1 hour MRS simulated spectra of a quasar at redshift 7 with a magnitude of 20 in 4.5 microns. I use a template from a low-rated quasar spectra. And we see that for 1 hour observation, we can detect the continuum of the quasar and also the bright emission lines, the hydrogen and also the helium ones. And this will open the possibility to derive black hole masses from quasar at redshift higher than 6.5 with H alpha and also Pachern lines. And this is the summary. The thing that I would like to bring with this talk is that MIRI brings unique capabilities to study the high redshift galaxies. Then I present the high redshift spectroscopy ETO program and some examples of the MRS ETO sources that have been star-forming galaxies and one quasar. And I would like to thank, and of course, questions. Thank you.
Thank you very much, Javier. So just while waiting for a couple of questions, how rapidly is this data, this GTO data, going to be made publicly available?
The GTO data?
Yeah.
Will be 1 year.
Okay. And there's a question here from Renske Smith. Do you expect to be able to do kinematics with H alpha in B14?
It's possible. If these have some outflows, maybe we'll be able to detect something. Yes, because we have, as I commented in the talk, the resolution will be close to 100 kilometers per second. If we have kinematic higher of this 100 kilometers per second, we'll be able to resolve the H alpha emission line and make some kinematics, work some kinematics.
That's great. We don't have any more questions right at this second. So I do encourage you to post any more questions on Slack, and hopefully Javier will be able to respond to them later. Okay, so we can keep to time now by moving on to the next talk, which is from Kirit Karkare, who is going to tell us about enabling the next generation EoR surveys with on-chip millimeter wave spectrometers.
All right, can everyone see this and hear me?
Yes, we can see and hear you.
Excellent. Okay, so thanks to the organizers for setting all of this up and to all of you for sticking around to the end of the day. I'm Kirit Karkare. I am a postdoc at the University of Chicago. I'm going to take us on a bit of an instrumental detour and tell you about the work that we've been doing on the experimental front here at Chicago to enable future large-scale millimeter wave surveys at high redshift. So of course, everyone here knows this, but it's always good to start with a summary of the state-of-the-art probes of reionization. So here's a schematic of the different phases of the universe. Of course, time progresses to the right. So on the left, after the hot Big Bang, universe expands and cools. It recombines to form hydrogen atoms and the CMB. And then we have the dark ages. Eventually, small inhomogeneities in that neutral hydrogen begin to collapse. And then they form the first stars and galaxies within the first few hundred mega years. And those sources start to pump out UV photons into the IGM, driving, of course, the major phase change, the epoch of reionization, sometime in between redshift of 15 to 6 or so, in which the IGM becomes ionized. We've learned about this process through a couple of probes. Number one, large-scale CMB polarization. This gives us a measure of the optical depth to reionization. We've learned about reionization through absorption features in quasar spectra. And we've learned about individual high redshift galaxies that can be detected with Alma or Hubble. But I think to really understand the global properties of reionization, including the complicated interaction between the ionizing sources and the IGM, we need to measure emission from this time on much larger scales. We want measurements that are sensitive to objects of all sizes, not just the extremely bright individual galaxies. And of course, if you're measuring just one observable, such as say 21 centimeter, you're not getting the whole picture. You want to have as many probes as possible. And so most of the effort for large-scale EOR studies has gone towards 21 centimeter experiments like PAPER, MWA, HERA, eventually SKA, are promising to use tomographic line intensity mapping to first measure the power spectrum and then eventually image the neutral hydrogen at high redshift. This is going to tell us, of course, quite a lot, but I'm going to argue that for a complete picture of reionization, we also need to directly measure the contribution from the luminous sources, from those first stars and galaxies themselves. And so just as an illustration for the complementarity of these measurements, we have here a simulation from Adam Lids showing the early star-forming galaxies on the left, the ionization field they produce, and a tracer of star formation such as CO. And you can see that that has some complicated interaction with the 21 centimeter signal. So as I just alluded to, what would be a good complementary probe of the Epoch of Reionization in addition to the H1? As many people here know, making measurements in the millimeter wave range of the spectrum is a good way to detect early star-forming galaxies, which likely played a major role in reionization, right? So in these early galaxies, you're making a lot of young stars, and so these things are emitting in the UV. And when you have star formation, you have dust, right? And that dust absorbs that UV and optical and re-emits in the far infrared. And so generically, if you look at the SED of one of these galaxies, you will get a bump in the SED at about 100 microns, as shown on the upper left here. That's due to thermal dust at 30 to 50 Kelvin or so. And so now you place that galaxy at high redshift, say in the Epoch of Reionization, and that bump is shifted over to several hundreds of microns. And so you see why millimeter wave measurements are useful here. Now, on top of that dust continuum, atomic and molecular species in the ISM also emit emission lines. So if you can identify such a line, of course, you get a redshift, and this is the crucial bit for understanding the dynamics of the EOR. In particular, there are a few lines that are commonly detected. I'll just mention CO, the J to J minus 1 rotational ladder gives you a nicely spaced series, probes the radiation environment of the galaxy with the ratio of the lines. And of course, C plus or C2, the 158 micron ionized carbon fine structure line, detected out to redshift 7 or so now. Okay, so you could say, well, we've been detecting these lines in EOR galaxies for years with ALMA. Don't we have everything we need? And I think the answer is no. The reason is that we really need large-scale measurements to learn about the global behavior of reionization. And so here is an illustration of what I think is a potentially transformative measurement. This is the cross-correlation coefficient of 21 centimeter and C plus, which we think traces star formation, as a function of redshift and of length scale on the x-axis. And so when you look at the cross-correlation coefficient, you can imagine them large scales on the left. Around galaxies, there's going to be a lot of C plus and a lot of ionizing photons, and so they're anti-correlated. But on small scales, H1 also lives inside halos, and so they're positively correlated. So this crossover point tells you something about the ionized bubble size. But now you look at the actual length scales, K of 0.1. That corresponds to something like a degree on the sky, right? So almost field of view, less than an arc minute without mosaicing. And so if you want to make measurements like this and eventually do serious cosmology at very high redshift, we need radically new instrumentation. These instruments need to be very sensitive. They need to have very wide bandwidth to cover large redshift ranges. And to measure large scales, they need to be optimized for faint diffuse emission, not for point sources or small fields like ALMA. You need to really think of these things as filled CMB focal planes, high detector count and sensitivity, but now you just need to add moderate resolution spectroscopy. So I'm going to tell you about our experimental effort to do exactly that. Our collaboration is called SuperSpec, primarily at Caltech and Chicago. The basic idea is that in millimeter wave spectroscopy, if you want both high sensitivity and wide bandwidth, you would usually use a diffraction grating. These things, unfortunately, are quite large. And so what we've done is taken all the good aspects of a diffraction grating, shrunk it all, and printed it entirely on a silicon wafer, just like a computer chip. So this immediately gives you huge space savings. To illustrate, on the left is a state-of-the-art grating spectrometer used by Time. Jason Sun will tell you about that tomorrow. And a single spectrometer takes up 700 cubic centimeters. We have fit the equivalent onto a 1 cubic centimeter chip. And of course, there are two things to remember. Our detectors are background limited, so sky sensitivity is just determined by detector count. And number two, The detectors need to be operated at sub-Kelvin temperatures, and you're limited in cold volume in these cryostats. So you can immediately see that going to on-chip technology is going to allow you to pack an order of magnitude more detectors in the same volume in your telescope, and that gives you the massive increase in sensitivity. I'll go quickly through this. The basic idea of SuperSpec is really simple. It is a filter bank spectrometer. So you have broadband radiation that comes in through your telescope, and it's sorted by a series of narrowband filters. And so in this diagram, I'm showing an input transmission line and a number of separate resonators. Each of those is tuned to a different lambda over 2. And so for each of your filter bank filters, you just tune that lambda to a slightly different wavelength. And those pick off separate frequencies and terminate in separate detectors. And so we have some simulations of channel responses for a couple of points. Our nominal observing band is 200 to 300 gigahertz. That gets you C+ at redshifts of between 5 and 9. And by appropriately overlapping filter profiles, you can achieve 80% or higher absorption across the band. For the last couple of years, I've been measuring these things in lab, evaluating the noise and spectral properties, figuring out an optimal way to read out the detectors. And so here we are measuring transmission spectra with some students. The detector's inside the cryostat there, and this is a Fourier transform spectrometer that's shining into the cryostat. We've shown that these devices work. So here's an example of spectra we measured of a 50-channel prototype device. So each detector indeed sees a different millimeter wave frequency. And we have 1 gigahertz resolution with this device. And so you can read about it in the instrument paper shown here. And the noise is shown to be low enough for ground-based observations. So we have the system that works in lab. Next, we need to show that it works on the sky. And so we're going to demonstrate our on-sky performance at the large millimeter telescope. The LMT is a 50-meter dish at 15,000 feet on the Volcan Sierra Negra in Puebla, Mexico. It will give us, it's a great source for, great site for point source observations. Status of the deployment. Pre-COVID, we were in the final stages of testing the instrument, and we had a ship date to the LMT in May, and so I should really be on the mountaintop right now taking data. So it's unclear when we'll get the go-ahead to go down there. But when we do, our primary goal is to show the SuperSpec can actually do science. So we're going to point at a few galaxies, high redshift galaxies produce a spectrum showing a line detection, and we think that will happen quite quickly. We're also deploying an entirely new instrument with entirely new detectors, and so we're going to be spending a lot of time to understand whether the noise performance is optimal and feed that back into detector development and to develop things like calibration routines. Again, this is a totally new detecting technology. So as soon as we're allowed on the mountain, we'll have a lot of data to analyze. Of course, we're not stopping there. This is the first step on the path to instruments that can make that cross-correlation with neutral hydrogen that I showed you earlier a reality. So the LMT is going to be good for detecting the individual galaxies. It's not optimized for large-scale intensity mapping. So many of us on SuperSpec are also associated with South Pole Telescope. We think this is an ideal platform for an intensity mapper. And so we're now proposing for a Pathfinder instrument on the SPT, which I call SPT Slim, the Summertime Line Intensity Mapper, to demonstrate intensity mapping with these new SuperSpec detectors. And so we think that in 2 years, we can deploy an instrument with a factor of 6 more spectrometers than we have right now. And so this would show that this technology is ready to do the kind of science that this community is interested in. Eventually, I think on a 5-year timescale, we'll be able to outfit the next generation South Pole Telescope focal plane entirely with spectrometers. And so this would be an extremely powerful instrument with sensitivity not just to detect those ionized bubbles and cross with 21 centimeter, but also to do some serious cosmology at redshifts higher than those accessible by galaxy surveys. Now, for example, you could constrain the BAO at redshift greater than 3. Okay, so I'll leave my summary here. I hope I've convinced you that millimeter wave spectroscopy is going to be an important part of understanding reionization, but we desperately need more sensitive instruments, and SuperSpec technology is, I think, getting us there by shrinking detector size. And we're going to have some pretty exciting results in the next few years. Thank you very much.
Thank you for that, Kirit. It was really nice to hear from a instrumentationalist after many kind of purely focused science talks for the day. So the first question is actually from me, and maybe this is just my ignorance of this side of the instrumentation, but the compact nature of the of the new system that you've got, does that have other advantages? So for example, does that make actually cooling the entire instrument much easier?
At some level, if you were to take the number of detectors that we can fit on, for example, a 6-inch wafer, and use gratings instead, you would not be able to build a single instrument that could cool it. You'd have to build several. So the basic idea is that since you are generally limited in cold volume, it is better to go compact. There is no real advantage in terms of the actual temperature to which you can lower it, because for ground-based observations, once you hit a certain floor, which is roughly 250 millikelvin, there's not a huge advantage in going lower.
Thanks for that. Dan Coe asks, how many nights will SuperSpec get? And how long does it actually take to get cool results once on the sky?
Right. So the number of nights is now up for debate. We had a few weeks before when we thought we were going to be the only telescope on the mountain during the summer months when the weather is not so good. Now that at earliest we will be on the telescope in fall, maybe. We will also be competing with other instruments like Toltec. So it's unclear, although I think we will certainly get enough time to at least show that the instrument works. And then later on, it will once we commission it, will be a competed instrument, just like everything else. Sorry, can you repeat the second question again?
So it's just a second bit. How long to get cool results once you're on the sky?
Oh yeah, I think that getting a basic result showing that we can indeed detect large numbers of Z of 6 galaxies with a 50-meter dish will be quite fast, on the timescale of several months. What I'm really excited about is understanding how to operate these detectors so we can build even larger focal planes, and going through the detailed process of understanding what is the physics that is limiting our understanding of the detectors is going to take much longer.
I think we've got time for one more question. This one's from Aprajita Verma, who asks, what mapping speed or typical survey areas can we expect for LMT and then the SPT campaigns?
Right. So I think for the super spec on LMT, we will really be talking. We will not be surveying wide areas. So I can't tell you a mapping speed off the top of my head because we don't really know what the atmosphere is going to look like there, and that could easily change by a factor of 2. What I can tell you is that we expect to be detecting C+ in a Z of 6 10 to the 13 solar mass galaxy in something like an hour to 2 hours. On the SPT, it's a totally different ballgame because we plan to be doing line intensity mapping there, and there I expect detecting CO, mid-redshift CO at 5 sigma in something like 100 hours of integration.
Okay, great. Thanks for that. So I think we've actually just passed 6 o'clock now. Sorry, 6 o'clock in the UK. So that is going to bring us to the end of Sazerac Day 1. So just thank you to all of the speakers again. So I'm going to turn my video back on now, actually. And just a couple of notices. So obviously only a relatively small fraction of people who applied for talks were able to get a live talk, just given the constraints in the sessions and the large number of submissions. So we did open up for anybody to submit a recorded talk. They're available, or a selection of them are available via the website at the moment. There is also a Slack channel, which we've just established for people to promote their recorded talks. Now, for some reason at the moment, I can't automatically add everyone to that channel. So I think at the moment, until I figure out how to do that, you might have to add yourself manually. But in that channel, do please go ahead and promote your own recorded talks and provide links to YouTube or our website. And again, there are the poster channels on the Slack as well, where we're encouraging people to post posters, slides and figures and answer questions around them. So obviously there's a lot more to Sazerac than just the live sessions going on each day. And obviously we'll keep all of this open beyond the conference. I don't know if Steve has anything else to say.
No, I wanted to thank everyone else again. I thought this was a really great day of talks, and I look forward to the next couple days.
Great. So hopefully we'll all see you back tomorrow at the same time. And then if you remember, on Wednesday, we actually have 2 sessions, one which is a little bit more accessible to our East Asian and Australasian colleagues. But yeah, look forward to seeing you all back tomorrow. And have a good day.
Thank you.
Thank you.